So now that we've covered some trig review, let's talk about trig substitution. So trig substitution is used when you have a square root. Typically when you have a square root in an integral, unless it's a basic like square root of x, it's hard. It can be harder to find an antiderivative. Now, you can easily find it if you can find a u substitution. So for example, if you have the square root of 1 minus x squared and you have an x on the outside, then you can use a u of 1 minus x squared. A du is negative 2x dx. And so if I divide both sides by negative 2, I get negative 1/2 du is x dx. So that means I can substitute in and get negative 1/2 the integral of square root of u du. And then I can find an antiderivative. Of course, u to the 3/2 times 2/3, and there's still a negative 1/2 out front. But if I don't have the derivative of my inside function on the outside of my square root, I can't use this u substitution. So for example, if instead I have the square root of just 1 minus x squared, what do? I can't use a u sub because I don't have the derivative of 1 minus x squared on the outside of my square root. So I need another technique. Now it would be nice if I could write 1 minus x squared as the square root of something. Because then I could take the square root of that squared something and the square root would cancel out. I'd have to worry about positive or negative, and we'll get to that, but for the most part, that square root goes away, and then I might be able to take an antiderivative. And in cases like this, we can write something like 1 minus x squared as the square of something if we recognize that this looks an awful lot like a circle, and that should make me think of trigonometric functions. Like this looks like an equation for a circle of radius 1, so maybe if I use trigonometric functions and some trig identities, I'll be able to do something about this square root. So first, we're just going to do an example of u substitution, and then we're going to talk about how to determine which trig to do. But we're going to use a trig and substitution. So we're going to sub in for x a trig function. In this case, we'll try sine theta. And what that's going to do is going to help us deal with that square root. So if x is sine theta, then dx is cosine theta d theta. Now, if x is sine theta, then I'm at some point going to want to use that theta is arcsine of x to get back to my x stuff, which means I only have the domain of my inverse function. So this only works for negative pi over 2 to pi over 2 for those angles. So I'll have to keep track of my domains and where this works out. But still, I can do this substitution. And like a u substitution, I need to substitute in for both my x and my dx. So I'll replace my x with sine theta, and I'll square that sine theta. I'll replace my dx with cosine theta d theta. Now it kind of looks like I made things more complicated, but I can also use trig identities, like the trig identity sine squared theta plus cosine squared theta is equal to 1, which means, actually I want sine squared theta. Oh no, yeah, I want that. I want that 1 minus sine squared theta is equal to cosine squared theta. So in fact, I can sub in for the 1 minus sine squared theta with cosine squared theta. And look at what I've done. I've used this trig substitution. I've substituted in for x a trig function like sine, and using a trig identity, I was then able to replace the 1 minus x squared with something squared, which then cancels with my square root. Now, we've talked a little bit about how we have to be careful in the trig review with a little algebra review. So we talked about how if I take the square root of x squared, if my x is negative, then I get negative x. If my x is positive, I get positive x. So I need to make sure that my cosine theta is positive, or I need to add in a negative sign when I take the square root of the square. But what I know is that theta is between negative pi over 2 to pi over 2. So what happens to cosine theta on negative pi over 2 to pi over 2? Well, it turns out that on negative pi over 2 to pi over 2, I'm always positive. So in fact, the square root of the square is just the positive cosine theta. And now I get the integral of cosine squared theta, d theta. At this point, I have to remember how to integrate cosine squared theta, and if you've seen integrals of trig functions, you know that a trig identity is how we integrate cosine squared theta. We replace cosine squared theta with 1/2 plus 1/2 cosine of 2 theta, d theta, which means I get 1/2 theta plus a simple u sub would give me 1/4 sine of 2 theta plus c. And now I've found an antiderivative for the integral of the square root of 1 minus sine squared theta cosine theta. But I started with the square root of 1 minus x squared. So what I would like to do is get back to my x. So I want to use the x is sine theta, or theta is arc sine of x, to replace. So I know theta equals arc sine of x. That's one thing. I also know x equals sine theta. And now I want to find sine of 2 theta. Well, I can use another trig identity. Sine of 2 theta is 2 sine theta cosine theta. And so then I get 1/2 arc sine of x plus 1/4 times 2 sine theta cosine theta plus c. And now I want to replace that. Sine of theta is, of course, x. But who's cosine of theta? Well, let's draw a triangle, a right triangle, involving theta. And sine is opposite over hypotenuse. Pythagorean theorem tells me that the adjacent side is the square root of 1 minus x squared. And so then cosine theta is adjacent over hypotenuse, or square root of 1 minus x squared over 1. And now I've subbed in for everything in terms of x instead of theta. So I have 1/2 arc sine of x plus 2/4 or 1/2 x times the square root of 1 minus x squared plus c. And that is trig substitution. In summary, I want to replace what's under the square root with something involving a trig function that allows me to write the whole thing as something squared, so when I take the square root, I can get rid of the square root.